Good morning, everyone. All right, good to hopefully you had a chance to enjoy the party last night, and thank you for coming this morning. My name is Camille Samaha. I'm with the Worldwide Public Sector Solutions Architecture team, and very honored and lucky to have Kartik Viswanath, product manager for EC2 networking, with us today. We're going to take a look back at Amazon Virtual Private Cloud over the last 12 months and see what features we've introduced, go into detail into some use cases that these features have enabled, and then just take a deep dive and talk about a couple of neat features that we, and particularly one that we launched yesterday. And Kartik is going to get us started.
All right, thanks, Camille. So quick show of hands. How many of you are rusty or not too familiar with VPC? Not familiar with VPC, so there's a few hands raising. For folks who are not too familiar with VPC, we're probably going to be running through some concepts of VPCs fairly fast. Folks are familiar with VPC, so don't worry, we're not going to be spending too much time with the concepts, but it'll just be a quick refresher and more along the lines to help us build the story on what we've launched. If you want to learn more about VPC, there's a NET301 session that's actually currently happening as we speak, but all our sessions will be available on YouTube. Give it a week or two. That's one session that I strongly encourage folks because there we actually do a good deep dive into all the concepts of VPC. The various building blocks for the VPC is dealt with in a lot more detail in that session. With that said, let's get started. VPC. Back in 2009 was when we launched VPC. Prior to VPC, we had what we now call as a Classic. This is basically, as you can see here, it's like one flat network. Every instance has a private and public IP address. The addresses never overlap, so anytime two instances want to talk to each other across accounts, it's simple, they can just talk to each other. That was Classic. And then in 2009, we launched VPC. VPC, as the name indicates, Virtual Private Cloud, you can create your own virtual network. A couple of data points with VPC is, if you have an account that you've created after December 4th, 2013, you are running on VPC. This is one question that comes up quite a bit. How do I know if my account can support Classic or VPC? Simple rule of thumb. If you created the account after December 4th, 2013, it's a VPC account. Another data point is all new regions moving forward will be supporting only VPC instances. We will not support Classic instances. Actually, even some of the regions that we recently launched, this is US East 2, Frankfurt, as well as the region in Mumbai. These regions support VPC-based instances only. We do not support Classic in those regions. With VPC, what we'll be covering today is 3 building blocks for VPC. The first one, addressing. How do you address instances in a VPC? We'll talk about security and what are the new features that we've launched in that space. And then finally, Camille will talk about connectivity. So we'll spend a lot of time in connectivity, what's the new we've launched relating to connectivity in a VPC. So first one. The fundamental building block for VPC when you talk of addressing is the CIDR block. As you guys probably already know, CIDR is basically giving you that range of IP addresses that a VPC can support. There's probably 2 best practices that I'd like to call out here. So in this example here, for the CIDR block that you have for your VPCs at 10.10/16, there's 2 components here. One is the actual 10.10, which is basically the address space. The reason this is critical is when you start having multiple VPCs, which Camille will go into more details, if the VPCs want to talk to each other, you have to think about overlapping CIDR blocks. So that's one aspect. So that you have to keep in mind. The second one is the /16. That basically is telling me what is the size of a VPC. And this is probably something in my 2.5 years here is stripped a lot of customers because there's 2 things that will happen. We've seen customers go define a /16, and then the VPC, the number of instances in the VPC is like 50 or 100. And then here they have a VPC from a CIDR allocation perspective. The usage is very low. And where it becomes more interesting is when you have a hybrid type of deployment, which is you have workloads running on-prem and you have workloads running on AWS. Many times you have these IT administrators are allocating CIDR blocks for your AWS. And now we've had customers come to us and say, wait, we created this /16 and our usage is super low and our IT administrator on-prem is not giving us more CIDR blocks because our usage is super low. So definitely take the time when you are creating your CIDR space for a VPC. You want to think about the addressing in general across VPCs. The second thing you definitely want to think about is what is the size of the VPC you want. The counter story with the /16 is I've had customers come and define a /27 and then I've run out of addresses. That gets a little bit more interesting because now they have to create another VPC, so the same service is running across VPCs, and now they have to start worrying about communication between the two VPCs. So definitely, when you're creating the CIDR space, do take the time to think about what is the size I need and the IP addressing. Pay attention to these because this will help you in the longer run. So that's on CIDRs. The next aspect with the VPC is this notion of availability zones. Today we have 14 regions. Every region has multiple availability zones. Think of availability zone more as an isolation boundary, right? So within, definitely if you're having an HA type of service, our recommendation to customers is you want your VPC to be running at least 2 availability zones. It's definitely a smarter thing to do when you want to have HA. We talked about CIDRs and what do you do with these CIDRs? So now you're going to start breaking these CIDRs into what we call as subnets. With subnets, one of the practices we've seen is customers use subnets as an isolation boundary as well. So what I mean by that is I can have a service that is running within a subnet. So I start running services within a subnet. That's one way we've seen a lot of customers allocate subnets. So that's at a high level in terms of with CIDRs. Let's see this key. So now once you have subnets, obviously the next thing is route table. So with every VPC, there's a route table. Like here in this example, you can see for the 10 dot, the target is local, which basically means all these addresses are local to the VPC. Quickly, one more aspect with the VPC is we also support DNS. What we do with the DNS is you can actually have the EC2 DNS name servers. The reason I mentioned that's a segue to what we've launched new in the last 12 months. First, let's look like we've launched a service in October of this year, which is basically adding DNS support to this. Is the EC2 DNS support for non-RFC 1918. Let's first look at what is non-RFC 1918 addresses. Your IETF, your Internet Engineering Task Force, they basically said, hey, we need these address space that are non-internet routable. Originally this was designed to protect the rate at which the IP addresses were being used. So they picked these 4 addresses, and another in simple layman terms, you can think of this as your private addresses. This is what you see most organizations use for their private networks. It's your 10./8 address, 172 as well as the 192 space. These are the 3 blocks of addresses that are used for, which are not internet routable. So prior to October of this year, we've had some customers, if you define a CIDR block that's outside of these 3, and if you wanted to use an EC2 DNS server, that was not going to work because we were not going to resolve those addresses. The workaround was customers had to actually use their own DNS servers. So this feature will now remove the need for you to run your own custom DNS servers. You can actually use the EC2 DNS servers. So now we will resolve all addresses. We're not restricted just to the 1918. Here's a quick, just an example of how if you use the dig. Let's see if I can get this. So if I do a dig trying to get the DNS address, you can see this is the DNS host name. Here, there's 2 callouts that I want to make here is, one is you can actually see for this DNS host name it is getting resolved to the actual address. as well as the .2 address. So this .2 over here. So very quick on that. I mentioned you have the EC2 DNS servers are supported as in the EC2 network. What we do is we take your CIDR address and we use the .2 address of your CIDR address as the DNS server name. All right, so on to the next topic, real quick on security. So with security, we support what's called as security groups. As the name indicates, it's basically a group of where you have instances which have a very, I would say, a common purpose. That's defined as part of a security group. Real quick on security groups, so you can have, there are rules in a security group. It's either /32, so you can define /32 rules, or you can define CIDR blocks in a security group, or you can actually reference other security group as well, which is particularly more convenient because as you start adding more rules, you don't have to go and update every single security group. So a very common practice we've seen with security groups is customers reference other security groups. That helps you from an operation standpoint. Manageability is a lot more simpler. Excuse me. Another point with security groups is it is stateful. And a good example would be is like you have ingress and egress rules. Let's say if you send a query out for a YUM update, when you get a response back, because I actually am I'm aware of the connection, I don't need an ingress security group rule for the traffic to come back. So by default with security groups, it is blocked at the beginning. So you have to start opening the holes. Think of it as it's completely blocked. With the rules is where you're opening up holes to let traffic in and out. So that's the quick update on security groups. For completeness sake, we also have network ACLs. It's similar to the ACLs that you're probably familiar with in the networking world. The key difference here is ACLs are stateless, whereas security groups are stateful. So what have we added in this space? Previously, you had the limit on security groups. This is probably one of the complaints we've heard from a lot of customers saying, hey, I'm running into a limit of 100 security groups per VPC. So we've increased that limit. Now the number is you can create up to 500 security groups in a VPC. I want to spend a few minutes talking about security group limits. The reason is this comes up quite a bit in terms of from a best practices perspective. Real quick, so we talked about the groups. There are two other concepts. One is the number of rules per security group. You can have 50 rules per security group, and you can also have the default is 5 security groups per network interface. A key number that you're going to be looking for is the multiplication of 50 and 5, which is effectively the number of rules per network interface. So you take your rules per security group and your security group per network interface, you multiply the two, that's the 250. And this 250 is the magical number. We've had a request where customers want more rules. So anytime we end up increasing your rules, we reduce the number of security groups that you have. Because the number that we're shooting for is you can't exceed 250. So now you can start playing with math. You can go 50 times 5. So you can go, I can have 100 rules and 2 security groups, or I can go 10 security groups and I can have 25 rules. So these are the two variables you're going to be playing with. But one limit is in terms of security groups per network interface, we cannot go beyond 16. So that's a hard limit that we have in terms of security groups per network interface. One very important point is when you're defining rules, please take the time to think about your IP addressing. The reason I mention this is I want to say at least about 75% of the times when customers call me and say, hey, I need you to increase my rules. When we looked at their config, what we found is they've defined a whole bunch of /32 rules, which could have easily been aggregated into a CIDR block, right? And we just go through their configuration, and in a matter of minutes, we end up reducing the number of rules they need, and they're happy. The reason I mention this is I've run into scenarios where I get paged on Friday at 5 p.m. and saying that, hey, I need you to increase my rules because we're launching the service on Monday and we're blocked. So definitely take the time. This is another area where I would recommend you guys take the time to think about how you're defining the rules. This goes back to the addressing because you can be smart about how you do your addressing. So wherein you're not forced to define these whole bunch of /32 rules. Instead, you can actually combine them, aggregate them into into blocks. So this way, you reduce the number of rules that you need. All right. So with that, let me hand over for the next piece, which is connectivity, to Camille.
Thank you, Kartik. All right, now that we have our VPC subnets and EC2 instances in this virtual private cloud, we want to make use of this network and expose, for example, your web applications to the outside world. Now, this is where the concept of Internet Gateway, quickly talk about it. It is a VPC construct that is highly available, highly scalable, redundant service that we make available, and its main purpose is to provide connectivity between your resources in your VPC and the internet. So if you really break it down, it does two primary functions. As Kartik said, you have routing tables in your VPC and your subnets. The IGW, or the Internet Gateway, provides you a target in your routing table to which you can then put routing table entries. And it also provides that connectivity to EC2 instances that you have allocated public IP addresses to. In this example, 54.4.5.6. So if you have that EIP and that IGW in a particular subnet, that's what you often hear the name public subnet. That's what makes a public subnet, is you have an IGW in the routing table, and you have an elastic IP address assigned to one or more instances in that subnet. Private subnet is exactly the opposite. It does not have those two constructs, which is the IGW or the elastic IP address. So here's a look at the routing table. You'll see the local target, which primarily says that all traffic within the VPC stays within the VPC. And then the default route, in plain English, is stating that any traffic not destined to my VPC will go to the internet through the IGW. And you'll see the target is the IGW ID. All right, so what about those instances in your private subnets that need access to things like Linux repositories? We don't want to expose them and give them elastic IP addresses or public IP addresses. And the best practice, for example, for our database layer, you definitely don't want to have internet connectivity to the database layer. So typically, what has been a common solution is to utilize an EC2 instance running NET service, such for Linux IP tables. And then you assign an elastic IP address to that instance, and then you, in effect, point the default route from your private subnets to the NET instance ID, as I'm showing in this example. And that pretty much what is saying that anything that is not destined to my VPC will flow to that NET instance running the NET service to translate your traffic and connect you to the internet. Now, in December of last year, we introduced the VPC NET Gateway service. This eliminates the need for you to set up EC2 instances, configure them with IP tables or your favorite NET service, and worry about availability, scalability of that instance itself. With the NET Gateway is a fully managed service that AWS takes care of availability and scaling for you. So similarly to the EC2 instance, once you launch the NET Gateway, you will assign a public IP address to it, and then you will use it as a routing target in your private subnets routing tables to send, in this example, the default route will point to the NET instance ID. And it will have the prefix of NET and it'll be available to you in a drop-down as a target in your routing table. So let's take a little closer look to the NAT gateway service. As I mentioned, it's a fully managed service, and it does require you to allocate the public IP address so it can communicate with the outside world. Now, it's important to note that once you launch a NAT gateway, it's launched in a specific availability zone. And it is a highly available service, so you don't need to worry about configuring high availability or redundancy for that service. We take care of that for you. But if you're architecting, or if you wish to have an architecture that is not zonal dependent, or it's not, you need to have the architecture be persistent across availability zones, you need to launch a NAT gateway for each availability zone in your architecture. As I mentioned, the primary benefit of this service is the simplicity of it. We take care of all the scalability. It is a uniform offering, and by that, I will compare it to an EC2 instance solution. If you launch an EC2 instance as a NAT instance, you have to worry about, all right, which instance size do I pick? And once you reach a point where you're saturating that particular instance and you need to increase the size, you have to worry about scaling up, and you have to do it yourself. And you also have to worry about single points of failure. You want to deploy a solution to ensure that if that NAT instance fails, you automatically bring up another instance, shift your route tables to that instance. So there's some complexity in setting up the high availability. With the NAT gateway service, we automatically take care of that for you. It's highly redundant within the availability zone itself. And from a performance perspective, the NAT gateway service supports bursts of up to 10 gigabits per second for TCP, UDP, and ICMP traffic. And if you do need or have a requirement for more traffic than 10 gig, then you can easily launch multiple NAT gateways and have additional 10 gigs per gateway. So there's no limit, or if there is a limit, it's a large number of NAT gateway services that you could launch. And from a security perspective, you can leverage network access control lists to authorize inbound and outbound traffic at the subnet level. So what I'm going to do is I'm going to defy the demo gods and see if I can do a live demo. If not, I do have backup screenshots. So bear with me. I just want to show you how easy it is to launch a NAT gateway. So if you go to the AWS console, and you just need to navigate to the VPC console, and on the left-hand side, you'll see the NAT gateways. All you need to do is, click the button to create the NAT gateway. You do need to associate the NAT gateway with a public subnet. A public subnet means that one that has an IGW attached to it in the routing tables. And in this case, I have them labeled to make it easier for me to select. The next step is to allocate a public IP address. If you already have one in your account, it'll be available in the drop-down list. Or if you don't, you can easily click the Create New EIP button to make one available to assign to the NAT gateway service. And off you go. It doesn't take that long to create. It's done. The only thing left at this point is to use that NAT gateway as a target in your routing table. So let's go and select one of my VPCs. Let me make sure I pick the right one. Here we go. This one does not have a default route, so it cannot communicate with the outside world. So you just add another route. You put your default route. And here's the NAT gateway as a target in your routing table. And we're done. Now, all instances in your private subnet have outbound access to the internet through the NAT gateway. And it's important to note that is outbound access only. The NAT gateway does not support connections being initiated from the outside in. So, let me switch back. And I'm going to go through the backup slides real quick. Here we go. So let's take a step back and take a look at the differences between EC2 NAT instances and the NAT gateway service. With the EC2-based NAT solution, you have full access to the operating system. What that means is you can configure the NAT service any way that you wish. You have the full control to configure that service. The downside, as I mentioned, is there's complexity to ensure high availability. There's complexity to ensure scaling of that solution to meet your bandwidth requirements. On the other hand, with a NAT gateway service, the software running on the service itself is optimized for NAT. It is fully managed and scaled by AWS on your behalf. But you do need to keep in mind, as I mentioned, it's only outbound traffic. So you cannot set up port forwarding to, like in a DMZ environment in your a traditional data center where you do port forwarding to a service behind it. This is outbound only NAT service. And another thing that also is worth pointing out, it does not support TCP and ICMP packet fragmentation. Okay? All right. I am going to quickly talk about VPC endpoints for S3. Traditionally, I talked about it in a similar session last year, but I'm only going to spend just a few seconds on this. Traditionally, to access your public service endpoints for S3, you have to have an IGW in your subnet and an elastic IP address, or you have to go through a NAT gateway service as an example. Now, with VPC endpoints for S3, gives you the ability to reach your S3 buckets and objects through the endpoint itself without having to assign a public IP address or an IGW in your VPC. So the traffic will flow to your S3 resources without having to attach the IGW. Now, if you look at the routing table in this case, the VPC endpoint is a routing target that has a prefix of VPCE for VPC endpoint, and you can add it to the routing tables in your subnets to route traffic to the S3 resources. Now, the service comes with a rich set of controls from a security perspective. You're able to leverage S3 bucket policies on the S3 endpoint side, and you can also define and attach IAM policies on the endpoint to limit which buckets or objects are accessible through that endpoint itself. So a rich set of security comes along with the VPC endpoint service. And quickly, another point, as you'll see, the destination in the routing table is what we refer to as a prefix list. What that means, the S3 endpoints are public endpoints, and we have multiple IP addresses associated with those endpoints. And over time, those might change. The prefix list is a mechanism to shield any of those changes from you. It's completely transparent to you. You use the prefix list as a destination, and you don't need to worry about what's going on as far as which IP address CIDR blocks we assign to our S3 endpoints. It automatically takes care of that for you. So it makes it a lot simpler to operate and manage. Now, the reason I spent a little bit of time on S3 endpoints is in combination with the NAT gateway, that enabled several of our service teams to develop features that they were not able to do prior to having those two capabilities. I'm going to spend just a little bit of time talking about those use cases. First one is the ability to launch Amazon EMR clusters and private subnets. EMR is the managed Hadoop service that we offer for data analytics. Prior to this launch, you had to launch your cluster in a public subnet because EMR has this minimum requirement to be able to access S3 buckets to be able to put service logs in there. Now, with the S3 endpoints being available, what we've done is the service places an ENI in your VPC that is owned by you, but managed by the EMR service to provide connectivity from and or between the EMR web service and your cluster running on EC2 instances. And with that conduit in place, then we can leverage S3 endpoints to access S3 objects and resources through that endpoint without having to define an internet gateway. Now, there are features with EMR, such as EMR FS, which is the EMR file system. That requires access to both S3 and DynamoDB. DynamoDB is a NoSQL managed service that we provide. In that case, in addition to having the S3 endpoints to access the S3 objects, you need a NAT gateway or even an EC2 instance running NAT. That would work as well to be able to access the public endpoints for DynamoDB. But regardless, your EC2 cluster is running in the private subnet. Another capability that the VPC features enabled is allowing your Lambda functions, and Lambda, in effect, it's just the ability to have your code defined as functions run on AWS without having to have EC2 instances. And those functions are triggered by events such as changes to an S3 bucket or maybe a DynamoDB table. Super powerful if you want to run microservices or serverless architecture. With, I believe it was in February of 2016, we launched support for accessing resources within your VPC from your AWS Lambda functions. Again, it's leveraging ENI to give you access to resources such as your RDS databases, an Elasticache node, or a Redshift data warehouse services. It also allows you to access services that you might be running in a private subnet within your VPC itself. And again, since we are within the VPC, we can leverage S3 endpoints to reach data repositories running on S3. And if you do want to have access from the Lambda function to public endpoints or the internet itself, then you can leverage NAT gateway to reach those resources from within Lambda flowing through your private VPC. One last use case, that was launched recently in September, I believe. It is Redshift enhanced VPC routing. What that does is allows, or when you turn on enhanced VPC routing with Redshift, and like I mentioned, Redshift is a managed data warehouse service that we offer. Any copy or unload traffic is then restricted to flow to the S3 repositories through your private subnet. And if those repositories are in S3 buckets in the same region, that traffic is forced to go through the S3 endpoint. If they are in a different region, that traffic is restricted to flow through your private subnet and leverage the NAT gateway service to reach those buckets. So lots of capabilities we were able to develop because of the features that VPC has made available over the past 12 months. All right. Let's take a quick look. We've talked about internet access and internet communications from your VPC. What about communicating between two VPCs themselves? A VPC is a virtual private cloud, and by default, it has no access to the outside world. With VPC peering, it gives you the ability to peer two VPCs and have them communicate with each other without having to flow through an IGW on each side. The way it works, and again, this is just a quick 30-second review, is let's say VPC A owner would initiate a peering request to the owner of VPC B. Now, VPC B can be in the same account or a completely separate AWS account. If the recipient owner accepts that request, then a peering connection is made, and the two VPCs can communicate to each other. And if there's, of course, the requirement that they cannot have overlapping IP addresses. And just, again, taking a quick look at VPC A's routing table, you would put the destination as the CIDR block of the remote VPC, and the target is a peering point itself. It has a prefix of PCX. All right? And basically, in English, any traffic destined to that remote VPC will flow through that peering connection. Now, in March, we launched the support to be able to reference security groups between peered VPC. Now, that's super important. I think Kartik mentioned it before. Prior to this release, you had to, and I'll put it up there, you had to use CIDR blocks from the remote VPC to try to restrict inbound and outbound traffic to particular resources in VPC A, for example. That could get really cumbersome. For example, you add a different subnet in VPC B, you add additional EC2 instances, and you had to keep on continually update your security group rules with those CIDR blocks. With this new capability, now all you need to do is put the resources in the remote VPC in a security group, and then you can reference that security group in your rules in VPC A. Greatly simplifies the management of your security groups with VPC peering. Another feature that we launched in July is the ability to support DNS resolution across peered VPCs. By that, let's take an example in VPC B or the right-hand side where you have an EC2 instance with a public IP address. If it has a public IP address, it's going to have a public DNS host name. If you do a DNS lookup from the left VPC, this is before the feature was released, using the public DNS host name of the EC2 in the peered VPC, you're going to get the public IP address back. Since it's a public IP address, is not any traffic flowing to that IP address will not traverse the peering, because the peering is between the private CIDRs between the two VPCs. With this new feature, you're able to leverage the split horizon capabilities of the native EC2 DNS service, and the DNS lookup at this point will give you the private IP address, and then you can leverage the peering connection. So this feature greatly simplifies your DNS configuration in a peered VPC environment. All right, something that we are really excited about, IPv6 support for EC2 instances running inside of a VPC. This was launched yesterday in the Ohio region, and regions all around the world are to follow. They're coming soon. So super excited about it. It took a lot of hard work from the VPC team and EC2 networking team to get this released. So there were 2 sessions that were opened up yesterday, an hour after we launched this. One was an introduction to IPv6, and the other one was a deep dive. Both of them are going to be available online within the next week or two, including the slides themselves. So that'll give you the ability to go in there and take a deeper dive look. I'm only going to spend a few minutes today on this just to give you the high-level feature set that comes with this launch. Now, this is a dual stack solution for now, so you'll have IPv4 and IPv6 in your VPC. When you enable IPv6, we're going to assign a /54 CIDR block of globally unique addresses. That's a lot of IP addresses. And each subnet will get a /64. A /64 has that many IP addresses. I'm not going to even attempt to read it. So that's too many commas for me. I don't even know what that is. I don't know. So it's just a lot of IP addresses. You'll be able to leverage the same security features that you're familiar with, security groups, NACLs, and flow logs. From a connectivity perspective, communications within the VPC between instances that can happen. I mean, of course, that's supported with, at IPv6, so using the IPv6 stack, leveraging the Internet Gateway to communicate with the outside world. This also supports direct connect to your data centers, as well as VPC peering. There's this concept that we've introduced of ingress-only Internet Gateway. With IPv6, there's no NAT. All addresses are globally unique that we assign. So we wanted to replicate the ability for you to have private subnets and only establish outbound communication to the internet. And this is where the egress-only internet gateway construct comes into play. I'm going to have an illustration of it. I'm a visual person, so maybe some of you are as well. I'll have it on the next slide to explain it a little more. Now, I just want to point out some things that are not yet supported as of the launch, but as things that we are working on. Those are VPC endpoints, don't support IPv6 today, VPN connections, and DNS resolution. So there are more things that we are actively working on and hopefully will have available to you shortly. Another point, IPv6 is supported by new generation EC2 instances with a couple of exceptions, and those are M3 and G2 instance families. So otherwise, other than those exceptions, all current generation instances support IPv6. Let's take a look now at the visual representation. Here's a common setup where on the left-hand side, you have a public subnet with EC2 instances that have EIPs assigned to them, and they're able to reach the internet leveraging the internet gateway. You also have a NAT gateway service, which provides outbound connectivity to EC2 instances that are residing in the private subnets, in this case on the right-hand side. If you enable IPv6, basically the VPC itself will get a /56, and each subnet will get its own unique /64. And then the EC2 instances running in the public subnet will get this globally unique IP address. Since we have an internet gateway associated with that public subnet, you'll be able to leverage that IGW as a target in your routing table to have traffic to and from the internet using IPv6 to that instance. Now, the EC2 instances in the private subnet will also get a globally unique IP address. But since there's no IGW associated with the routing table of that subnet, it cannot communicate to the internet, and connections from the internet cannot be initiated into it. But we cannot leverage the NAT gateway to have access to Linux repositories, for example. This is where egress-only internet gateway comes into play. You can set one up and give outbound-only access to EC2 instances in your private subnet to the outside world. Okay? Let's take a quick look at the routing tables. You'll see support both IPv4 and IPv6 destinations in the routing table. On the public subnet on the left-hand side, both IPv4 and IPv6 have a target of the IGW ID. On the private subnet for IPv4, the default route points to the NAT gateway ID. With IPv6, it'll point to the egress-only internet gateway ID. So, fully supported today in Ohio, other regions to come soon. With that, I'm going to hand it to Kartik to talk about EC2 Classic.
Thank you. Quick raise of hands. How many of you are still using Classic instances? There's a few of them. All right. Back in 2015, when customers wanted to move from Classic to VPC, actually I would say last 1.5 years, we've seen quite a few customers move from Classic to VPC. So rewind almost 2 years back. So the way customers had moved from Classic to VPC was you basically are setting up a public address and there's an IGW on the VPC, and using public IP, the Classic used to communicate to VPC instances. Obviously, it's not the most effective way because you're going on the internet. So Classic Link effectively was allowing private IP communication between Classic and VPC instances. What we did last year was we launched this feature called for DNS resolution over of your public host names to your private IP addresses over Classic Link. So the idea here is if you have workloads sitting on Classic that's running EC2 DNS, so you're resolving these addresses using DNS, and you have the same thing on VPC. Now, when these two instances are talking to each other, and if you want an instance, a VPC instance trying to resolve to an EC2 DNS hostname, and if it was going to go over Classic Link, what we would return is the public address, which is obviously not the most effective way how you want to communicate, because when you want to use the private IP for the Classic to VPC communication, with this DNS resolution over Classic Link, what it allows you to gives you is more flexibility when you're moving workloads from Classic to VPC. Another feature that we've launched is Classic Link over peering. I'll spend just a couple of minutes on this. So what you see on the screen here is your Classic. When you're having Classic and talking to VPC, you have Classic Link for communication. If you look at the VPC's routing table, you basically have a route entry for 10/8 pointing to the Classic Link. One thing we've seen with customers when you want VPCs talking to each other, or VPC peering is obviously the preferred way of communication. So when you were trying to move workloads from Classic to VPC, what we wanted to set up was a natural architecture for in your VPC world, where you're using VPC peering to talk for workloads within a VPC. But as you're moving workloads from Classic to VPC, with Classic, with a Classic instance, could only do a Classic link to a single VPC. Now, when you have an architecture with VPC peering, you obviously would want your Classic instance to be able to talk to multiple VPCs. And this is where a Classic link over peering actually comes in very handy, where now I have this one VPC that I'm Classic linking my Classic instance with, but then I have VPC peering set up on the other side, which is the natural architecture I want to get to. And as I'm moving workloads, it gives me the smooth migration from Classic to VPC. I'll spend, this is a very interesting use case. How many of you all attended the Netflix session yesterday? Okay, still see a few raised hands. Real quick, in a couple of minutes, what was presented. Netflix, back in 2008, they had a database issue, which they were running their own private data centers. They had a database issue, and that's when they decided, let's move to AWS. So they started their journey in 2008. They moved to Classic, and by 2012, they were running 100% on AWS. And 2009, once we launched VPC, they started seeing there were benefits to moving to VPC. About a year, or slightly more than a year back, they started this journey of let's move from classic to VPC. And if you look at their environment, they have 100,000 plus instances. They had numerous services. And more interestingly is numerous teams, dozens of teams, and each team had their own schedule and their own pipeline. So when they wanted to move, they could not align the teams to move all at the same time. So the approach they took was they basically looked at the type of applications. They start off with their non-critical applications. They moved those first, and they had to build a few tools because in an environment where you have 100,000 plus instances, there's a lot of tools. So they had to work through, there's some work from a tooling perspective, and that's why they start also with the non-critical applications. This gave them some learnings that, and they leveraged a lot of the features that we talked about here, both on the Classic Link side as well as on the VPC side, which helped them do their migration. Here's a graph that actually shows the actual migration in terms of instances. I'll leave you guys with this one data point with Netflix. In 6 months, they migrated all of their instances. If just looking at the sheer number of instances they migrated and the time it took for them to migrate, what they were effectively doing was in every 2.5 minutes, they were migrating one classic instance to VPC in 6 months. 2.5 minutes is one instance. That's the magnitude of instances that they had to migrate. And one thing that really helped them, and I think if you guys have a chance, I would recommend you guys taking a look at their session as well. It's how they talk in detail about how they leveraged pretty much all the features that we talked about today, in the last 12 months. They leveraged those features to help them migrate from Classic to VPC. All right, with that, please do complete your evaluations. And also, these are some of the other related sessions that probably would be helpful for you guys. Questions?